Nuclear power has played an important role in supplying the energy source since the middle of the 20th century. However, the reserves of uranium used for the fuel of a nuclear power plant is very limited. This feature strongly drives us to find countermeasures in resolving the urgent issues regarding the depletion of the world's fossil fuel reserves. Fortunately, a sodium-cooled fast reactor is now being developed, and it imposes an efficient uranium utilization and contributes to the security of a sustainable energy supply. Now let us introduce you the Korean sodium-cooled fast reactor system. The reactor core producing fission power consists of several fuel assemblies. Upper internal structure called UIS provides the primary coolant flow path and supports control rods as well as instrumentation cables. The cylindrical support structure protects the reactor core and provides significant functions to prevent the reactor vessel from direct contact of hot sodium. Two centrifugal sodium pumps are located around the reactor core. These pumps circulate the primary sodium coolant effectively. Now you can see intermediate heat exchangers transferring heat from the reactor core to the intermediate sodium loop system. These are internal parts and components inside the reactor vessel. Their compactness makes a highly economical design possible. All the internals and major components are safely isolated from the environment by the reactor vessel and the head structures. The next view is the constitution of the Intermediate Heat Transport System, called IHTS. The IHTS consists of the steam generator, mechanical sodium pump, and the connected sodium pipings. A compact piping arrangement achieved in this system benefits the maintenance and repair work, and this feature also makes the system economical. At this point, let us show you how this reactor system produces electricity. The main heat transport system, composed of the primary and intermediate heat transport system, uses liquid sodium as a coolant. The secondary system provides the function of electricity production by using a steam Rankine cycle. In order to enhance plant safety, the intermediate heat transport system is employed to prevent an unexpected chemical reaction between radioactive liquid sodium inside the primary coolant system with the secondary water, steam. The primary sodium is effectively heated by the core fission power during normal plant operation. The heated sodium coolant flows into the intermediate heat exchangers and then returns to the reactor core by the primary sodium pump after heating up the intermediate loop sodium. The intermediate sodium coolant flows into the steam generators along the hot leg piping and converts the feed water into high-quality steam. The produced steam moves successfully to the auxiliary building and rotates the turbine generator to produce electricity. After this process, steam is converted into subcooled water at the condenser unit, and it returns to steam generators by the feed water pumps. The Korean sodium-cooled fast reactor system has been designed by employing highly reliable and safe features. Now let us show the representative passive decay heat removal process during a postulated design basis accident. For example, a loss of normal heat sink caused by a station blackout. If a station blackout takes place, the operation of all circulation pumps is suspended. Then the control rods rapidly drops into the reactor core and ceases fission reaction immediately. Since the core decay heat is steadily generated even after the reactor shutdown, the system heat load should be safely removed until the power supply is normally recovered. However, since the normal heat transport system is not available in this event, a passive decay heat removal system starts its operation based on the unique hand-owned design concept. This system, called PDRC, removes the residual heat effectively by a heat exchanging mechanism coupling with the density variation of the sodium coolant. Consequently, the core decay heat can be continuously removed into the final heat sink, that is, the atmosphere, without either operator's action or any power-operated components. The feature, totally based on a passive mechanism, makes the peak cladding and coolant temperatures below the design limit at all times.